All right, ladies and gentlemen, today's class recording has started. So, as I mentioned at the beginning of class when we were going over where we're headed over the next couple days, our next 4 days is going to be devoted to the study of stoichiometry. That's it's fun to say, isn't it? Right? Stoichiometry. Okay.
Not anymore fun than Romulus or Plasma's motto.
All right, so as you can see from the first part of your outline, when we talk about stoichiometry, we are going to be doing mass and mass and quantity relationships among reactants and products in a chemical reaction. So instead of just talking about what is present, we're going to talk about how much is present. Okay? So mass and quantity relationships among reactants and products in a chemical reaction. All right, good? What? Helps with the recording. So. All right, good? Good? Okay, so just a little more detailed, right? Stoichiometry is the calculation of quantities of substances involved in chemical reactions. What we'll find is that when we have a balanced chemical equation, it's not just showing the conservation of mass that happens from beginning to end. It's also giving us a recipe for the ingredients that we need to make a certain product. Okay? For instance, let's go here, and yeah, we can use this. No, let's not use that one. That one's hard. Okay. Yesterday, all right. So yesterday, we used this equation as an example of a type of reaction and the energy that's associated with it. First, what type of a reaction is this? This is a combustion reaction. Right? This is a combustion reaction because one of your reactants is O2. One of our reactants is reacting with oxygen. Okay? And then, I don't want you guys do this because it's on the board right next to you. It's just a person watching the recording can't see this. We went through, and in order to balance this equation, we added this set of coefficients. Okay? Good? All right. So, let me use an example. Any of you ever see The Martian? Okay. So The Martian with Matt Damon, right? For those of you that haven't seen it, I won't give you a total spoiler alert, but he gets stranded on Mars by himself, and he has to learn how to survive. So one of the things that he does, and this is funny part right at the beginning, is he makes himself a little garden, right? Using his own poop and mixing it with dirt from Mars, okay? But one of the things that he needs in order to make the garden work is water. Does anybody remember how he gets the water for his garden? Okay, Kate, do you remember?
I think he dug down and
No, that's not how he got the water for his garden.
I'm not sure exactly how he did it, but he made a contraption in the center of his thing, and he mined stones and set it on fire.
Good. He basically used the fuel that from one of the rockets or something like that, and he had a combustion reaction going. Because what's one of the products of this combustion reaction? Water, right? Every time we burn something, for the most part, especially hydrocarbons, which a lot of fuel is a hydrocarbon, one of the products is always water. And they showed him, and we don't need to do this, but he did some calculations to figure out how much water he needed to produce to keep the certain moisture content of the soil, and that translated into how much fuel he would need to burn, right? So, while this is an equation that represents what happens in a combustion reaction, it's also a recipe. These are ingredients. These are products. If we know that we need to make a certain amount of one product, we need to know how much ingredients, or how many and how much of each of those ingredients we need, right? So this chemical equation, balanced form, said it doesn't just tell us what's happening, it also gives us ratios between the different ingredients, okay? So, if we had to describe the ratio, how would we describe the ratio of the reactants of this reaction? Let's see if we can use proper terminology to describe the ratio of the ingredients. Anybody want to give it a shot? Well, that is balanced. With those coefficients, this is balanced. All right. So this is propane. How many molecules of propane do we need to make this reaction work? Just one, right? We didn't put an extra coefficient in front of it, but the fact that we wrote the formula down to begin with implies that we at least need one of them, okay? What do we need to react this molecule of propane with? Oxygen, good. Let's see if we can be a little more descriptive. 5 diatomic oxygen molecules, good. So, the ingredients for this recipe include 1 molecule of propane and 5 molecules of diatomic oxygen. Okay? And what do we get when we react those molecules together?
H2O.
4
Water.
molecules of water and 3 molecules of carbon dioxide, right? So if you have a recipe at home, it says you need this many ingredients, right? 2 cups flour, 1 cup milk, whatever it might be, blah, 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 blah. And then at the end of the recipe, it usually says, makes 2 dozen cookies, or whatever, right? That's what this is telling us. What ingredients do we need, and then what are we going to get out of it? Okay? We just have to know how to read the recipe in order to know what we need. Okay? So, balanced chemical equations through their coefficients indicate the ratio of moles of reactants to products. Ooh, there's a blast from the past, right? Moles. Ooh. Okay. All right. Do we have this written down? Balanced chemical equations, through their coefficients, indicate the ratio of moles of reactants and products. Okay? All right. So going back to this balanced chemical equation, we said that the ingredients to this reaction are 1 molecule of propane and 5 molecules of diatomic oxygen. Can we isolate 1 single molecule of propane and 5 diatomic oxygen molecules? No, way too small, okay? But we introduced a tool long ago that can help us. We talked about the mole. Does anybody remember anything about a mole from when we talked about it before? Okay.
It's used to count matter.
It's used to count, let's stop the statement there. It's used to count, okay? What's true about a mole of anything? Will, do you want to throw it?
How do you remember that?
Okay, so 1 mole of a substance, or 1 mole of anything, no, not yet, this is just kind of a reminder, right? So if you want to, you can kind of do it in the space to the underneath where that nitrogen reaction is right there. There's kind of a big space in the middle, so we're not going to write a whole bunch in that space. Okay? All right, 1 mole of anything always contains the same number of things. So, we can't isolate a single molecule of propane or 5 molecules of diatomic oxygen. But we can, through some calculation and measurement, measure out 1 mole of propane molecules. 1 mole of propane molecules would contain this many propane molecules. So if we know that we have 1 mole of propane molecules, how much oxygen would we need? How many times 6.022 times 10 to the 20? 5 times that many. Because we have 1 mole of propane, but for every 1 propane, how many oxygens do we need? 5. So if we have 1 molecule of propane, we need 5 molecules of oxygen. If we have 1 mole of propane, how much oxygen do we need?
5.
5 moles, because we always have the same number of things. We can't get 1 molecule and 5 molecules, but we can get 1 mole and 5 moles. Okay? So we're going to use the idea of a mole always being the same number of things to keep the ratio that our chemical equation is telling us. Okay? Good? For starters? All right. So let's take a look at a chemical reaction down at the bottom of the page. Okay? N2 plus H2 equals NH3. First, without knowing anything about the reactants or products of this reaction, you should be able to tell me what type of a chemical reaction this is. What type of chemical reaction is this?
Synthesis.
This is a synthesis reaction, right? We're taking small things, we're putting it together to make something bigger. NH3 isn't that much bigger than N2 and H2, but it is bigger, all right? Is it balanced the way that it is currently written? No, it is not, right? So fortunately for you guys, I was feeling generous, and I gave you that balanced equation right next to it. Okay? So, what is the balanced equation telling us about this reaction? Or more specifically, about the ingredients of this reaction? Scott, go ahead.
There are 3 hydrogens and 1 nitrogen.
3 hydrogen
Molecule.
for every?
1 nitrogen molecule.
Good. We need 3 hydrogen molecules for every 1 nitrogen molecule. But what else could that be telling us?
3 moles for every 1 nitrogen molecule.
We need 3 moles of hydrogen molecules for every 1 mole of nitrogen molecules. What will we end up with at the end of this reaction? 2 moles of NH3 molecules, right? These coefficients are giving us the ratio of ingredients, either in the reactants or the products, with how we go from one to the other. Okay? Let's go ahead. They can, right? They can mean molecules if we're talking about it on a very small scale, but they can also mean moles because 1 mole of something is always the same number of things. Doesn't matter what it is, it's always the same number. So those coefficients are ratios of molecules or moles, depending on what we need for our situation. Okay? All right, good? Okay. Let's take a look at the first example down at the bottom of the page. Okay, we're going to skip Roman numeral number, or we're going to skip like Roman numeral 2, A and B. That's just kind of the steps. Let's go straight to C. So it says, in a space station, carbon dioxide exhaled by astronauts can be removed by a reaction with lithium hydroxide. This reaction produces lithium carbonate and liquid water, which could be good because we could use that to drink because we need that water on the space station and stuff like that. Okay? So, question number 1 says, how many moles of lithium hydroxide would be needed to remove 20 moles of carbon dioxide, which is the average daily amount that's exhaled by a human? Okay? All right, this is a practical application. If we want to go long-term space travel, right, this is a problem that we face. Every time you take a breath, you breathe in oxygen, you exhale carbon dioxide. That's great in the short term, but if you're in an enclosed space for a very long amount of time, right, what's going to start happening to the amount of oxygen in that enclosed space? It's going to decrease, and then what's going to happen to the amount of carbon dioxide? All right, so we got to have a way to try and reduce the amount of carbon dioxide while maintaining the amount of oxygen. Look. Plants do this, okay, but plants don't do it. So plants, through photosynthesis, use carbon dioxide to then they use carbon dioxide and they make sugar and oxygen, right? But 2 things wrong with that. 1, it's kind of slow, and especially for the amount of carbon dioxide that's being exhaled, right? And 2, what else do plants need in order to do that reaction? Sure, that is a possibility. But again, with the enclosed space that we have, having enough plants in that space for them to reduce the amount of carbon dioxide naturally, that's not quite practical. It would help, and especially too because if we could grow plants, then we have other things to eat and stuff like that. But overall, with the rate that we're exhaling carbon dioxide to the rate at which the plants remove the carbon dioxide from the air, we have to do something artificially to make sure that we don't go over that level of carbon dioxide that's dangerous to humans. So you're right in that naturally that's how that process occurs, but in an enclosed space in a spaceship, it doesn't happen quite fast enough. We have a problem. So that's one of the problems that's one of the factors that's contributing to global warming is that by deforestation, right, by us artificially removing forests for farmland and timber and places to live and stuff like that, we're removing plants from our environment that naturally take out carbon dioxide. Carbon dioxide is a very strong greenhouse gas. I say that because you don't have to know how it works, but if I say greenhouse gas, does that make sense? Right? It's one of the gases that's contributing to global warming. So not only are we increasing the amount of carbon dioxide that we're putting into our atmosphere by using cars and things like that, we're decreasing the plants that naturally take it out of the atmosphere. So that's that's not the only reason, but those are 2 factors that are contributing to our changing climate. So yeah, so if we take out all the trees, we're in trouble. And we are doing that at a faster rate than we should be to clean up the carbon dioxide that we're putting into the atmosphere. So it's fun. It's definitely fun. So. Good. something. We are very close to permanently damaging our environment to a way that we can't fix it. So we're really, really close to that point. Like we should have been doing stuff for the past 20 years that we haven't been doing. Well, okay. Federal government officials aside, we are actually doing more than some other countries are doing, especially when we consider how much carbon dioxide we're putting into the atmosphere. We put a lot of carbon dioxide into the atmosphere, but we are trying to make steps to change that. But there are other countries around the world that are in a phase of their economic growth that they just want more cars, more industry, and all this other stuff. China. India. So, well,
But we also
yeah,
don't
but
want-
yeah, but like, okay, hey, it's cool. China wants to be a really developed nation, and India wants to be a developed nation, but at what cost? Like, if we, pollute the environment so much that you're a developed nation on a planet that doesn't hold life, then it really doesn't matter.
It all comes together and make a civilization than Mars,
So,
than other places.
I mean, you see,
One problem with that, no longer.
yeah, we've.
The other problem,
So
no
you have to
offices
create a
cooperate.
Okay, so, but let's talk about this immediate problem that we have here, okay? So, let's go through this problem sequentially, okay? And we've done this before, let's do it again, okay? The first step to any problem should be what?
Wait,
No,
next part,
no,
Underlining.
no.
figure out what that is.
Figure out what it's asking for. What is the question that we're trying to answer? So, what is the question that number one is asking us to answer?
How many moles of lithium hydroxide?
How many moles of lithium hydroxide? Okay. Oh, I will tell you this. From the, for this part, for this section of the unit, I will give you formulas and equations. You don't have to figure them out on your own. Okay. So lithium hydroxide is LiOH. Okay. So this question is asking us how many moles of lithium hydroxide would be needed. That's the question that we're trying to answer. Okay. So we've asked a question. What's the next step in the process?
I thought lithium hydroxide is hydroxide.
It depends on what it's attached to, right? Aluminum hydroxide is AlOH3 because aluminum has more valence electrons than lithium does, right? So yeah, so Zach, this is the hydroxide part. How many of them are there depends on what it's attached to, okay? All right, we have a question. What's the next step in the process? Before we answer the question, what? Think about the question and come up with a plan, right? If we're talking about scientific method, right, it would be a hypothesis, but our hypothesis is based on facts, laws, and theories. Yes, does that all sound familiar?
Yes.
Facts, laws, and theories are information that we have to work with. What's one piece of information that they gave us to work with in this problem? We know we're trying to find out how many moles of lithium hydroxide, but they told us that we have to get rid of 20 moles of carbon dioxide. Right? That's how much we have to get rid of each day. Okay? All right. Next, even though they didn't specifically say it in a form that is useful to you right now, what is this opening paragraph describing? A space station. What can we do on that space station? Make drinkable water in the process of doing what?
Whatever it's called, synthesis, removed by reaction.
We can make water while removing carbon dioxide. Okay. All right. So here they're giving us a description of a chemical reaction that will result in carbon dioxide being removed. What are the reactants of this reaction that they're describing in the paragraph up at the top of the screen? Nope. Those are not the reactants. Those are the what? Those are the products. Katie, what are the reactants? Good. Carbon dioxide can be removed by a reaction with lithium hydroxide. Those are the reactants of this reaction. That's what we're starting with. All right? Elizabeth, what do we produce in this reaction? Lithium carbonate looks like this, and water looks like this. Okay? Even though they didn't specifically give us a chemical equation, they told us how we're going to make that chemical equation. Okay? Now, before we can use that chemical equation, though, what has to be true about it?
Balance.
It has to be balanced. Is it balanced the way that it is written?
No.
No. Okay? So, remember we talked about ways to balance chemical equations? We should start with elements that only show up in one formula on each side of the equation. So for this reaction, what element should we not start with?
Oxygen.
Don't start with oxygen, all right? That's usually a good idea in any type of balanced chemical equation. Don't start with oxygen. Start with other stuff. All right, so carbon. Is carbon balanced from left to right?
No. Yeah.
Yeah, carbon's good, right? Is lithium balanced?
No.
Nope, lithium's not balanced, right? Okay. So in order to balance the lithium, right, we're going to have to put a coefficient of 2 out in front, just like that, right? That increases the number of lithiums to 2. That matches over here, okay? But that also increases the number of hydrogens, right? How many hydrogens are there on the left-hand side now? 2. How many are there on the right-hand side? 2. So that's good. All right. So we're good with carbon. We're good with lithium. We're good with hydrogen. Let's go oxygen. How many total oxygens on the left? 4. 2 here, but then 2 here as well, right? Because we get 2 of those molecules, right? How many total on the right? 4. All right. So we're good now. Okay? Okay. We know what we have to start with. We know what we have to get rid of. We now know how we're going to do it. So let's use that information to figure out how much lithium hydroxide we need. Stoichiometry problems are conversion problems. Conversion problems get rid of bad units and leave us with good units using conversion factors. We know we have 20 moles of carbon dioxide, but we don't want 20 moles of carbon dioxide, so we're going to go time sign fraction bar. Right? If you want, you can put that over 1 to make your math seem a little bit easier if you would like. Okay? When we set up conversion factors, we go units first. What unit should go on the bottom of this conversion factor? Green. Moles, but moles of what? Moles of carbon dioxide, because that's what we were given. So we're going to put moles of CO2 down here. Formulas are very important when we're doing stoichiometry problems because we're going to use different parts of the equation or compare different parts of the equation. So we're trying to get rid of moles of carbon dioxide, so that's going to go on the bottom. What unit should we put on the top of this conversion factor? What are we trying to get here? Moles of lithium hydroxide. That's going to go on the top. What part of the chemical equation tells us the comparison of moles of one thing to moles of the other thing? What part of this chemical equation allows us to compare the amounts of one thing to the amounts of the other thing? What part of the chemical equation?
Reactant.
The coefficients of the chemical equation compare the amount of one ingredient to the amount of the other ingredient. What is this equation telling us about the ratio of carbon dioxide to lithium hydroxide? 1 to 2. We need 2 molecules of lithium hydroxide for every 1 molecule of carbon dioxide. But guess what? If we need 2 molecules of lithium hydroxide for every 1 molecule of carbon dioxide, we also need 2 moles of lithium hydroxide for every 1 mole of carbon dioxide. Here's moles to moles, right? So we're going to use our coefficients to fill in the numbers to show us the ratio between these two. What number should go on the top of this conversion factor? 2 should go on the top, right? And then what should go on the bottom? 1 should go on the bottom, because that's the ratio between moles to moles. Okay? Okay, go ahead. Okay. Mathematically, that kind of comes out when you do the math, so you don't have to. Let's stick with the coefficients as they are written in the chemical equation, because like I said, mathematically, that's all going to come out in the wash anyway, you know. So yeah, stick with just what the coefficients of that chemical reaction tell you. Go ahead. No. Those coefficients give us ratios of any part of this chemical equation. Okay? So we're not going to get to it today because we're going to run out of time. But here, how many moles of water are produced? We'd still start here, but then we'd put moles of carbon dioxide here, but we'd put moles of water on the top, because that's what this is asking us for. Those coefficients work whether we're comparing reactants to reactants or reactants to products. It's still the ratio of what is each part of that equation.
So if there are 4 coefficients, do we add them?
No, because usually you're only going to compare 2 things in that equation. You're not going to compare more, right? So yeah, here we're just comparing carbon dioxide to water. Here we're just comparing carbon dioxide to lithium hydroxide. So you'll only use 2 coefficients at a time. Okay. All right, good here? All right, so just in case, right, real quick, moles. Okay, so this weekend, the other sheet that I gave you today are problems similar to this. I have given you equations for all of the reactions within the problem, but those equations are not balanced. So you will need to balance them before you use them to find the ratio of moles, okay? So answers to that sheet will be posted on the calendar, so you can check out how you are doing. Have a good weekend, everybody. I'll see you on Monday.